Hi, our group is me, Megan, Yibo, and Z, and the title of our project is Coping with High Dimensionality, Statistical, and Data Science Methods for Revenue Optimization. So a little bit about the motivation and background. Slacks on Racks is a client of Buxton, and they're interested in knowing how a variety of demographic and geological information will help in determining the location and revenue of their next retail store. There are 5 potential stores that they want to know the expected sales of. So in order to do this, we've developed some statistical models with prediction accuracy and interpretability. We were provided with a very informative and high-dimensional data set, which contains 73 observations and 445 explanatory variables. So, the curse of dimensionality, what is it? It was coined by Richard E. Bellman when he was considering problems in dynamic optimization, and the definition of it is the various phenomena that arise when analyzing and organizing data in high-dimensional spaces that do not occur in low-dimensional settings, such as the three-dimensional physical space of everyday experience. So an easier way to think of that is when a data set has a large amount of features but not as many observations, which is what we're dealing with here. So looking at the picture at the bottom of this slide, we see that in the first dimension on the left, it's really easy to capture all of the data, but as we move into the higher dimension spaces, it becomes harder to capture every single data point. So the mean absolute percent error, or the MAPE, is the criteria that we're going to be using in order to measure prediction error, and ideally we would like it to be close to 0, and the formula for it is displayed here.
There are several remedies we can use, both parametric and non-parametric. First, here we use principal components analysis as a parametric way to do the regression. The principal component analysis is a good dimensional reduction method which can help us to generate the key factors from a dataset with large amounts of variables. A traditional principal component analysis procedure is applied to this dataset after missing the clear. To be honest, we do this analysis twice. First is on the whole dataset, and second is on the subpopulation of the dataset, which has been grouped by key factors like education level and race and some other things. After that, we extract information from the principal components and decide to fit data with multiple linear regression with both variables and components. As you can see from the picture, we get a model with 7 key variables which are all significant. The adjusted R-square of the model is 88.7%, and the mean absolute predictive error is 12%, which is sound and reasonable. Also, from the model, we can see the variables include square feet, open year, and labor or some other things. We know that from common sense, they are all related to the sale price, and it makes sense that we use them to explain the sale price.
Linear model is very nice, but there is some observation being as a contaminates in our regressions. That's why we introduced robust regressions. Out of those 73 observations, actually 4 of them all tends to be very similar, and they were labeled as outliers. That's due to the special correlations, which could be very suggestive in the site selection. And we're gonna show here just to say those 4 need to pay more attention to. A non-parametric as a remedy, it's a very good in the prediction with a better accuracy, but at expense of the coefficients. Namely, we have no clue about what's the coefficient like linear model gonna be for every factors, and we have proposed random forest regression, Bayesian support vector machines, and the GUIDE names guide, and the multivariate adaptive regression Splines Mars. Out of them, Bayesian is kind of very kind of a lot of tedious words, and we skip that, and then we decide to use random forest and Mars as our non-parametric models. So the random forest one, see here for the subpopulation A with less than 20,000 square feet area, we have the about 7.13% of the MAPE rate, which can be very, very good as compared to the linear model. And for the population B, which is area larger than 20,000 square feet, it's like about 2%. The thing is, you can see here, some of the observations, I can say majority of them get underestimated in the model A. Then we move to the Mars model and we cross our fingers, think it would be better performance, and turns out it is. And you see here, for the subpopulation A, the MAPE reduced from 7% to 1.6%. And from the MAPE, it's actually achieved at about 5%, which is very promising.
So a little bit about our results. Considering our multiple linear regression model and the random forest model, there are multiple variables that we believe are the most important in selecting the new location and predicting revenue, and they're kind of described below. Two that we find extremely important is open year because it overlapped between both models, as well as the blue-collar labor within a certain amount of driving distance from the location. So we find those two variables extremely important, also including the other ones. So we would like to acknowledge Professor Sadler and the Statistical Science Department and thank the other teams who provided insight and expertise and greatly assisted with our research. Thank you.